These ones, they taste sour.
This call is now being recorded.
Right? And said, on the other hand, these guys, they taste bitter. And they are usually, they have like a soapy feel. Or texture, if you can call it that. And then what happens as well was we said an acid, if you put it on a litmus paper, if you remember a litmus paper or a litmus test, you just take this other paper. It is sensitive to both acids and bases. So you dip it inside the acid or the base, assuming you don't know whether that thing is an acid or a base, and you dip it inside there. And depending on whether it turns red or blue, you will be able to tell whether the contents of the beaker or whatever are acidic or basic. So with acids, it turns red, right? Blue litmus paper turns red. While with, are you saying something?
No, sir.
Oh, it's like you're talking, there's some sounds there. Oh, but it's fine. Just try mute yourself. I don't know, maybe your little siblings are somewhere there. Anyway, so we said if you have blue litmus paper, it will turn red if you are checking for whether that the contents of a beaker are acidic or basic, right? And then for a red litmus paper, if you are testing for base, it will turn blue, right? So basically, you don't use the same litmus paper to test for bases and acids. Excuse me. So turns, oh no, this is black. Quick. We said it turns blue. Litmus. You remember litmus paper, most litmus paper.
So you said.
And then this one, I was asking if you remember a litmus paper. Do you know a litmus paper? You don't know? If you, or you, right, that's good. And I don't have to explain what a litmus paper is. It increases the concentration of hydrogen. So that's another nature of bases. What happens is in a solution, if there's an acid, hydrogen ions will increase, or if you add an acid. What that does as well is, since there should be equilibrium of some sort between the hydroxide and hydrogen ions, once you increase the hydrogen ions, it will decrease the hydroxide ions. So let me show you. So hydrogen ions are represented by H+, right? And then OH ions, say, reduces. So you see, it's counter. Okay, reduces OH in a solution. So usually hydrogen ions help us measure just how acidic or basic a solution is, especially if you're conducting pH calculation. The concentration of the hydrogen ions will tell you whether that solution is basic or acidic. So a high concentration of hydrogen ions results in an acidic solution. You will know that, I think, in grade 12, when you use the concentration of hydrogen ions to calculate the pH of a solution. But essentially, that's what happens. And then if there's more hydroxide ions are these ones. So that means that solution is more basic, right? So that's why an acidic solution will have less hydroxide ions, because the more there are hydroxide ions, the more basic that thing is, which is not ideal for an acidic solution. Right. The opposite happens for bases. They actually reduce H plus or hydrogen ions in a solution, while they increase the OH ones. So you see, increase in a solution. So one thing to know, whenever you think base, think OH minus. Whenever you think acid, think H plus. Right. Then one last thing is that pH, if you remember pH, the pH here is less than 7, while the pH there is greater than 7. Bases have a pH greater than 7. Remember, 7 is the neutral value. So if you have a scale like this, 7 is here. Anything that side is acidic, while anything that side is basic. Right, so just for you to remember, I'll do this. H plus hydrogen ions, 0H minus hydroxide. Just giving you the names in case you might forget. All right, so this is basically the difference you know from the previous grades between acids and bases, right? So then now we have typical acids that I would like you to remember off by heart if possible, right? Typical acids include let me write it here with black. So you would have something like HCl. Should I write the name? Let me see. Okay, let me write all of them. Right, so you would have HCl, hydrochloric acid, and usually they have a certain strength. So this is called a strong acid. Then you would also have H2SO4. This is called sulfuric acid. They will usually give you the name of the acid during the exam, and then give you also the formula. But for the most common acids, you'd have to know the name and the formula. So I think when I send you these notes, I'll also include the name. Just for the sake of time, I'll only write the formula for now. But when I send you these notes, I'll also add the names. This is nitric acid. It's also considered a strong acid. Then you have phosphoric acid, I think is HP. Usually this one is considered a weak acid. Then you should have something like carbonic acid or oxalic acid and so on. Another one that we might have is there's an acid called ethanoic acid or acetic acid. You write it CO. This one is also another weak acid. Excuse me. Right. And then you might have carbonic acid, another weak acid. So ideally, you should know all of these off by heart, right? They shouldn't confuse you when you see them in an exam paper or whatnot. These are typically all the acids that are likely to be in your exam. You won't find anything outside this, right? So if you remember all these acids, you'll be fine. So these are your typical acids. Now let's go to your typical bases. So your typical bases, also with bases, there are strong bases and there are weak bases. So let me write it here. Right. Typical bases or usual bases include, the most commonly used one is sodium hydroxide. Right. Sodium hydroxide. Okay, let's do this. Base. Strength. Now, so you change my color. Sodium hydroxide is a good one. This one is a strong base, has a high concentration of hydroxide ions. You have another strong base called potassium hydroxide, very strong. You have another base called calcium hydroxide. I hope you can see the trend with strong bases. They have OH, right? This is another strong base. You have another, what's this? Base called ammonia. Very common, this one. Ammonia. Ammonia is a weak base. It's a very strange base, actually. We'll get to it, though. And then you have sodium carbonates and 2CO3. So sodium carbonate is another weak base. Then what you would also have is, let me do this. My table is, okay, don't know why it's doing that. Okay, never mind that. And then you have another one called sodium bicarbonate. Sodium bicarbonate is basically baking soda. So they can say baking soda or sodium bicarbonate. So baking soda is just basically for baking. This one is a weak acid as well. And then we also have calcium carbonates. Calcium carbonates, the typical name for it, or the most conventionally used name, is limestone. So if you know these by heart, you'll be fine. Because typically these are the acids and bases you would likely come across in an exam, a test, or whatever assessment, really. So now let's get to how we actually define bases in grade 11 and going forward, right? Okay, let's see. What did I do here? So what happens is we have two theories that are used to define acids and bases. Theories are called the Arrhenius or Arrhenius, I don't know, and also the Lowry-Brønsted. Each of them a color, just so that life is more interesting. Right, so there are two theories that are used to define acids and bases. So these theories are namely the Arrhenius, like I said, theory number one, Arrhenius theory, and you have theorem number two. I might have made this a bit too big. Much better. So you have the Arrhenius theory, and you have theorem number two, Lowry-Brønsted theory. Now, each of these guys define acids and bases differently, right? So let's start with Arrhenius. So Arrhenius theory says acids, right? So Arrhenius basically says that acids, it's just a substance that produces a hydronium ion whenever it's in an aqueous solution, while a base, a substance that produces hydroxide ions whenever it's in an aqueous solution. However, the issue with this theory is that it only limits acids and bases to an aqueous solution. That's why most of the time we prefer theorem number two. So we mostly use this one. Okay. So this one says acid and then base. So it says an acid, any substance that produces a hydronium ion. Hydronium is written like this in an aqueous solution. Aqueous, okay, this is a tricky word. How do you, yeah, it should be like this, aqueous solution. Right, that is an acid. Now, a base, on the other hand, is a substance that produces hydroxide ions. You will have to memorize these definitions because you might be asked on an exam. Some exams, they might ask you, what's the Arrhenius definition of a base? What's the Arrhenius definition of an acid? Right, so base is a substance that produces sorry, hydroxide ions in an aqueous solution. This word aqueous is very strange. It's an interesting English word, I mean. So that is what Arrhenius's theory says. Reason being is because Arrhenius noticed that bases, or rather water, let me say water splits up into hydronium and hydroxide solutions. So let me move this up there. So Arrhenius noticed that H2O, or water, splits up, or rather, in scientific terms or chemistry terms, it dissociates into two separate ions according to this equation. So the equation I'm referring to is the one I'm about to write now, which is H2O, right? Notice these arrows. These arrows means the equation is reversible. It can go forward and backwards. All right. H3O plus, right? This is ion number 1, right? Plus OH minus. This is ion number 2. Notice these AQs. AQ means aqueous solution. This is my L. It's not an E. I know it looks like an E. It's actually an L. Right. So AQ just stands for aqueous, or aqueous solution. Right. So he noticed that this is what happens. However, it has a limitation. It only explains acids and bases in an aqueous solution. That's why we prefer the Lowry-Brønsted theory, right? So because the Arrhenius does not explain to us what happens when the acids now and bases are not in water, they are not dissolved in water. What happens then? So it limits this thing to bases that are in an aqueous solution only, and it also limits bases to hydroxide only. But we also know that not all bases have hydroxide ions. For instance, if you remember very well, NH3 does not have hydroxide ion, and it's a base. Sodium carbonate as well, sodium bicarbonate, calcium carbonate, they don't have OH, and they are also bases. So you see, that's why we prefer the Lowry-Brønsted theory. So what does it say? What does the Lowry-Brønsted theory say about acids? And it's such a very simple definition. These guys were very simplistic in terms of defining what acids and bases are. So here's how they define acids and bases. They said acids are proton donors and bases are proton acceptors. So acid and when they say proton, they are referring to H plus, this thing. This is our proton, is a proton donor. While a base is a proton. Do you see how simplistic this definition is? Arrhenius, on the other hand, told us about hydronium ions dissolving in an aqueous solution. You see, that was even a longer definition than this one. But these guys, on the other hand, they came up with a very simple definition. Acceptor. There's no way you would struggle to remember that a base accepts and an acid is the one that donates. Donor means donate or give away for free, right? So this is how they described acids and bases, right? So notes, process by which, so the process by which an acid and a base interact such that one donates an electron, a proton to the other, is called proton transfer or protolysis. Protolysis process you will see this a lot, this word protolysis, protolysis. But yeah, that's the process by which the acids transfers electrons to, protons to the base, and the base accepts protons from the acid. Right, this is basically how it works. That's the simplest definition that Lowry-Brønsted gave us. So he also said, or they also said, another thing to remember right? So an acid usually ionizes in water or in an aqueous solution, because they were adding up as well to what Arrhenius has already established. Remember, in science, you don't start from scratch unless you are talking about something that has never been discovered. If someone comes and presents an idea scientifically, all scientists that are interested in that study, they question the idea, they make sure that the law or theory that this person is kind of trying to come up with or they have proposed is actually true. So they test it so many times. And then if it has limitations like Arrhenius, they build onto it and then they try to make sure that whatever was introduced by the initial idea actually covers a broader spectrum of all possible scientific fields out there. So what I mean by that is, for instance, Arrhenius explained it in aqueous solution. So now Lowry and Brønsted took that definition, they built on it, and they said, well, we also noticed that acids will, according to Arrhenius, ionize, while bases, they dissociate. So dissociate is to split up. That's what dissociate means. Ionize, we'll see what that looks like. So examples. Here's a quick example. Right. So if you have hydrochloric acid, we know it's an acid. Should I use black? Let's try black. HCl plus water. What will happen? According to Lowry-Brønsted, because HCl is an acid, it will donate the proton. Proton, remember, is H plus. So it will donate that H plus and it will be left with Cl minus. Right. However, water will gain that donated proton, and now it will have H3O plus. So this is how a typical Lowry-Brønsted interaction between an acid and a base would look like, where HCl is the acid and H2O is the base. So what ends up happening here is you now have what you call conjugate acid-base pairs. So what that looks like is, or what it means is, just because this is an acid here and this is a base here, when you get this side, this becomes the acid and this becomes the base. Right, because you can reverse the reaction. If you take the reaction from the reactant side, for instance, and you are reversing going to the other side, H3O will donate to Cl minus to form HCl and H2O. So that's what it would look like. Quick example. This is an example of, let's say, now a base dissociates. Right. So how a base dissociates, for example, is if you have, remember our famous base, NaOH, it would dissociate. Remember, to dissociate is to split up into sodium ion plus hydroxide ions. Right. So why do acids ionize while bases dissociate? Right. The reason for this is acids are molecular structures that are covalently bonded together, while bases, they are ionic structures. So remember, covalently bonded means it was both non-metal. Excuse me. Right. While ionic structures, it was mostly ions that led to the formation of that substance. So one ion donated an electron to the other ion, and then it resulted in the formation of that substance. Right. So that's why you can sort of split them. So that's why a base dissociates. While acids, on the other hand, they ionize. because they don't split into different ions. So some official definitions for ionization and dissociation are that, well, in ionization, like I've already said, it's a chemical process where covalent molecules produce ions in a solution. So that's the reason the acids will likely ionize, because they are covalent molecules. So we'll say while dissociation now is when ionic compounds produce ions in a solution. So you see, you just change covalent molecules and you put ionic compounds. It's easy to memorize these definitions rather. Where ionic compounds or molecules, actually compounds, produce ions in a solution. Right? So now I wanted to, before we move on from these examples, let me do this. mentioned something here, but I didn't put it down. So these we'll talk about in our next lesson, acid-base pairs, which let's say we'll discuss later. They are very easy though. It doesn't work very nice. So this produces what you call acid-base, conjugate acid-base pairs. So we will talk about these at a later stage. Let me just highlight them for you. Yes. So now this is how an acid ionizes. As you can see, HCl with water gives you Cl minus and H3O plus. Right, so there's only one acid. I mean, no, not acid. One base does not dissociate. Remember we said acids, they ionize while bases dissociate. There's only one base that does not dissociate. The reason for this is because, remember we said the ionization is because these are ionic compounds. Now this base, however, it's not an ionic compound, right? So that's why it does not dissociate. So let me show you. Ammonia. That's the base that under no circumstances will it ever dissociate. Right. So, except weak bases actually. Let me just put it like that, weak bases, because there are other bases that don't dissociate. Like right. Because it's not ionic and it is not polar covalent. Remember, we said it must be covalent. So, e.g., I like making examples. If you have ammonia, you'll find that it does this. So, before we close this lesson, I want to highlight something here. Okay, you have this, right? And then we said this is a base. And then let's call this guy. Okay, I don't think you can see that yellow. This is an acid. Right, so check this. It does not dissociate because it is not ionic and it is not polar covalent. What it does instead, it ionizes, right? As you can see in this example. Right, so another thing I want you to notice, okay, let's do this. If you note H plus, acceptor, and then H2O, proton donor, in this case. Another note. This is our last note. In our previous equation, water was not an acid. Come here. Check this. Water was not an acid. This is an acid. And this is a base. Water was not an acid. It was a base. Now, suddenly, water is an acid. What do we call substances that can switch between either being an acid and a base? We call them ampholytes. Okay, let me just copy this equation so that you see. While 2, let me take this one. You see how water was an acid and now it's a base. You probably know this already, but we call such substances ampholytes or ampholytic ampholytes. So ampholytes, so that's pretty much what we have for you today. So basically, this substance, water, in this case, is called an ampholyte. Now, water is not the only ampholyte that exists out there. When I send you these notes, I'll add the other ampholytes that you might find. I remember I remember HSO4 minus is one of them. Right, so water is not the only ampholyte out there. There's a dozen, there's dozen being and obviously an exaggeration, but there's more ampholytes out there. Right, so yes, that's what I wanted you to know for today. And then on our part 2, I want us to cover more examples with past paper type examples. Right, for now, consider this an introduction into acids and bases.